All right, so we'll see how this goes. Um, I decided to try a little different way of uh, recording this. So let's take a look at 3.4. So in 3.4, we're taking a look at applied maxes and mins. Let's see if we get a good focus on that. We're just going to keep going out of focus. Let's see if we can lock that in. Oop. Okay, I think that's going to be about best. So I wanted to just take a quick look at that activity from the book. So we have this rectangular shape box that we're going to mail, except that the end is going to be a square, so it's x by x. And then, so let's call the width y. And we're told that the this box with a square end is going to need, the post office says that the length plus the girth should be less than 108. So what does that mean about this box? So the girth is the perimeter of the side here. So that's going to be 4x, right? And so if you take the sum of the 4x plus the y, that needs to be less than 108 by post office rules. Okay, so we'll say that 4x plus y less than or equal to 108 for USPS. Oops. That's the problem with having my picture up here. Well, let's see how we do anyway. So now we want to try to, with this restriction, find the maximum, or the box with max volume. Okay, and so let's see, the volume of the box then is going to be x by y. Well, before I say that it's just a function of x, right now the volume is going to be x squared times y. But then we have this restriction on it, right? And so from this restriction, we can say that y, if we maximize, we can probably assume pretty safely that the maximum is going to occur where 4x plus y is equal to 108, although that might be subject to investigation. So we'll take 108 minus 4x to be our y, and so my volume now as a function of x will be x squared times 108 minus 4x. Good. Just bringing the x squared through, because we're going to need to differentiate, right? We're going to take x squared times 108 and then x squared times minus 4x. I'm going to rewrite that minus 4x cubed and then plus 108 x squared. Good. So this is my function. Any restrictions on x? Well, if y is equal to 108 minus 4x, we better make sure that that's not a negative number. Okay, so therefore 108 minus 4x should be a positive number. I guess it could theoretically be 0. And so x is going to need to be less than or equal to 108. Sorry about that, divided by 4, which is 27. Okay, so we have a kind of a natural, I keep running into my picture. We have a kind of a natural restriction then that x needs to be between 0 and 27. Good. So now we have a function on a closed interval. So now when we try to find the global max, we can just compute it using a table, right? And the table will have our critical points and our endpoints. Good. So let's go ahead and compute the critical points. V prime of x will be minus 12x squared plus 216x. Okay, and now you could just set that equal to 0 and solve, because it is a quadratic. But notice that you could factor out a common x, and actually 216, or 12 divides 216, so you could rewrite that in factored form as 12x times, then this would have a x on it, and then this would be minus, let's see, 12 times 18 is 216. Did you know that? Set that equal to 0. You didn't have to know that. X equals 0 or x equals 18. Good, 0 is in our interval, in fact, so 0, 18, and 27. Okay, if I compute my volume with x equals 0, I get 0. And if I compute my volume with 27, that makes y equal to 0. And so my volume is again equal to 0. And so really, we could have any positive number here and we would get the maximum volume. And so I believe if you plug in 18, you get 11,664. Yes. So therefore, that's our global max. So if our box is 18 by 18 by 108 minus 4 times 18, good, so I think that was 108 minus 4 times 18 is 36. So our box is 18 by 18 by 36. Those are the dimensions that give us the maximum volume, given this restriction, right? Good. All right. I'm going to stop the recording here, and we'll try a new one.